Welcome to practice exam 4R. In this question, we're trying to figure out which of the following chemical species is the reducing agent. So I always start by writing out what it means to be a reducing agent. And that means we're actually looking for the chemical species that is getting oxidized. So let's go through and figure out what is being oxidized in this problem. So we can see our nitnium ion is going from 3 plus to its solid neutral state. So that means that the Nt3 plus was reduced, making this the oxidizing agent. Well, that's all well and good, but it's not what we're looking for. All right, now if we look at the manganese dioxide chemical species here, if we look at this manganese, it's in a +4 oxidation state because it's paired with 2 oxygens. Over in this molecule, it is in a +7 oxidation state because it's paired with 4 oxygens. Each oxygen has an oxidation state of -2, but there's an overall -1 charge. So all of the oxidation states need to add up to the overall charge. So notice what happened with this value. It went from +4 to +7. So this species was oxidized, therefore making it the reducing agent, which is what we're looking for in this problem. And it should be noted, if you're ever asked to identify a reducing agent or an oxidizing agent, you're always looking for something in the reactant side because it's the reactants that are actually giving up or gaining electrons. So it has to be one of the reactants. It's not going to be one of the products as our answer. So this question is a little bit wordy, but we can work our way through it. It says the chelate effect describes the tendency of polydentate ligands to form thermodynamically stable metal complexes with large formation constants. And so this is true, but let's talk about why it's true. So if we consider a transition metal complex, let's just pick randomly a cobalt-3 metal complex. Let's say we were to add in a polydentate ligand. I'm going to use ethylene diamine as an example. So ethylene diamine is bidentate. It has, that literally comes from the words meaning 2 sets of teeth because it's got 2 lone pairs of electrons on it. So when we add ethylene diamine to a solution that has copper 3 plus, for example, in it, both lone pairs of electrons can add themselves, can form this Lewis acid-base adduct with the cobalt 3 plus. So it's called bidentate because there's 2 lone pairs of electrons that are biting onto that central metal. So let's say we're looking at an aqueous solution of cobalt. So let's say we have this cobalt 3 plus. If it's in an aqueous solution, water will actually coordinate with the cobalt 3 plus because water is a monodentate ligand. So oftentimes 6 waters will swarm around our metal, and we would have this sort of complex. If we add in the ethylene diamine, because the ethylene diamine, each ethylene diamine, and so we call this En, each one donates 2 lone pairs of electrons, so we only need half as many. So we only need 3 ethylene diamines to donate in, or to add in. And when we do this, the ethylene diamine will swarm around the metal and will kick out the water. And one of the main reasons for this is because notice what happens when the water is kicked out. So we form our new complex, and 6 waters are released in the process. So we go from 4 moles of reactants to 7 moles of products. This is an increase in entropy. So that does indeed help make a more thermodynamically stable complex. Also, there's probability at work here because we only need 3 ethylene diamines to quote-unquote find that central metal. So it's easier for polydentate ligands to attach because you don't need as many of them to locate that transition metal cation in the aqueous solution. So that also adds to the favorability of these, which entropy is technically a function of probability anyway. So this is indeed true. These have very, very large Kf values. In this question, we're trying to figure out if something becomes more or less soluble when we add in another chemical species. So it's talking about copper hydroxide, and I suggest writing out the reactions that go with the solubility. With solubility, with KSP reactions, we're breaking these apart into their respective ions. So this would break apart into copper 2+ and 2 hydroxides. And the question says, when more solid CuOH2 is added to the saturated solution, the solubility of the salt increases. So if we add more of a solid, like this, will that solid push the equilibrium? Well, the answer is no. Remember, solids do not contribute to Le Chatelier's principle. So if we add in more solid, well, that's great. There'll be more solid, but that's not going to allow more of it to dissolve. If this is at equilibrium, if we don't do anything to change the concentration of aqueous species or gases, it's not going to shift. So this is going to be false. Adding in more solid is not going to change the solubility of the solid. This question says, how many electrons are transferred in the following redox reaction? And there's two ways we can look at this. We can look at either the oxidation or the reduction. I'm going to look at the oxidation here. So we're oxidizing this I-, and we're turning it into solid iodine. So each of these I-, we have 6 I-, and each one has a -1 oxidation state. When we're turning it into solid iodine, so the solid iodine is I2 solid. Okay, each of these has a 0 oxidation state on them. So that means that each iodine went from -1 to 0. So each iodine must have given up 1 electron. However, there are 6 of them. So that means that the iodine total, the iodides, gave up 6 electrons. If you want to think about it in terms of the reduction, we have nitrogen going from +5 here down to +2. So each nitrogen gained 3 electrons, but there are 2 nitrogens that did that. So again, it's 6 electrons. Whenever we have a balanced reaction, it has to be an equal number of electrons involved in the oxidation and the reduction. This question wants to know what is the oxidation state of chromium in the dichromate ion. So what I like to do, with oxidation states, it's good to have a bookkeeping system that works for you. I like to put individual oxidation states above the atoms in question. So for example, each oxygen is going to be 2- in most molecules. Now, there are exceptions, like, for example, peroxides and with O2 and oxygen pairs with fluorine. But for the most part, usually it's going to be in a 2- oxidation state. And since there's 7 of them, that means there's going to be an overall, when you count all 7 oxygens, there's going to be total oxidative state of -14 from all those different oxygens. Okay, so we need all of our oxidation numbers to add up to the overall charge on the molecule, which is -2. So what number plus -14 equals -2? Well, that's going to be +12. So that means that these 2 chromiums here are contributing an overall oxidation state of +12. But since there's 2 of them, we have to divide that number by 2 to get that each chromium is in its +6 oxidation state. And whenever you want to know oxidation state, it means the oxidation state on individual atoms involved. So the answer is going to be +6. Here we're calculating the E standard of a cell and then using that information to figure out if it's going to be spontaneous or non-spontaneous under standard conditions. So our first quest is going to be to figure out what the reduction and oxidation half reactions are. For the reduction, we're turning iron 3+ into iron 2+. And remember, standard potentials are intensive properties. So it doesn't matter what the stoichiometric coefficients are. All that matters are the materials and the oxidation states that we're working with. And using our handy-dandy table of standard potentials, we can figure out that the reduction half potential of iron 3+ to iron 2+ is positive 0.771 volts. Okay, great. Now, for our oxidation, we have our two H2O liquids, turning into H2O2. And two H pluses, and giving up 2 electrons in the process. And that comes with a price tag of negative 1.776 volts. Because remember, whatever we see on the reduction potentials table list, for the oxidation, we have to reverse the reaction and flip the sign. Okay, now, using the rule that the E standard of a cell is the standard reduction potential of whatever's being reduced plus the standard oxidation potential of whatever's being oxidized, we're going to add together these two values, and when we do, we'll end up getting that the E standard is equal to negative 1.005 volts. Okay, that's our standard potential. And remember, negative potential means a non-spontaneous reaction. Positive potential means a spontaneous reaction. So this is going to be answer A, negative 1.005 volts and non-spontaneous. Here we're trying to figure out which of these sparingly soluble salts are more soluble in acidic solution. So the rule that we need to invoke here is that salts with basic anions are going to be more soluble in acidic solution. So we're going to break these apart into their respective ions, and we're going to ask ourselves, is the anion basic? And if so, the answer will be yes, this is indeed more soluble in acidic solution. So the first one breaks apart into Au plus, gold cation, and Cl minus. Cl minus is the what of a what, therefore making it what. It's the conjugate base, quote unquote, of a strong acid, therefore making it negligible. So this one is not going to be more soluble in acidic solution. For what it's worth, Au plus is an acidic cation, but we're not looking at the cations in this particular problem. For the platinum carbonate, it turns into Pt2 plus, and carbonate, CO3 2 minus. CO3 2 minus, is it acidic, basic, or neutral? Well, it's got a negative charge, and it's not the conjugate of a strong acid, so this is indeed going to be a basic anion, which means this will be more soluble in an acidic solution. We'll do the same thing for silver hydroxide. These are some expensive salts that we're looking at here. So silver and 2 hydroxides. Are hydroxides basic? You bet they are. They're like pumpkin spice latte level. They're super basic. And then finally, we have copper fluoride, which would dissociate into copper 2 plus and 2 fluorides. And remember, HF is not a strong acid, so F minus therefore must be a weak base. So salts 2, 3, and 4 are going to be more soluble in acidic solution. In this problem, we have to find a KEQ, but we're only given a reaction. So how can we quantify this reaction? Well, it's a redox reaction, right? And how can we attach some numbers to this? By using our reduction potentials table. We can find the E standard. And remember, if you know the E standard of the reaction, the E standard of the cell, then we can figure out the KEQ using this equation. But first, we need that E standard of the cell. So that's precisely what we're going to find. Our reduction half reaction is going to involve the gold gaining an electron to turn into Au solid. And that's going to net us 1.69 volts. Cool. Our oxidation half reaction is going to be tin 2 plus, yielding, that's aqueous, tin 4 plus, also aqueous, and giving up 2 electrons. And that's going to be negative 0.154 volts. Okay, now in this particular problem, we do need to know N, which is the number of electrons transferred in the balanced reaction. So we're going to need to multiply everything up here by 2 in order to get a balanced half reaction. Great. Now we can combine these two together and get our overall reaction. And our overall reaction is, well, the one that we're given up here. And our potential is going to be 1.536 volts. Now we'll plug that in for our E standard. And that's going to be So we'll have 1.536 volts. And that's equal to our 0.0592, which is a constant, divided by N, number of electrons transferred in our balanced reaction, which, again, is going to be the 2 moles of electrons, then times the log of KEQ, which is what we're solving for. So multiply both sides by 2 and divide both sides by 0.0592. We get 51.89 is equal to the log of KEQ. Then we'll do 10 to both powers. And when we do, we'll get our KEQ, which is 7.8 times 10 to the 51st. In this problem, we're trying to figure out which one is the strongest reducing agent under standard conditions. Whenever I see oxidizing agent or reducing agent, I always write what that means. So if we're looking for strongest reducing agent, we're looking for which of these chemical species is most readily oxidized. Okay, so we're going to need to find the oxidation potentials of all of these. And some of them actually can't be oxidized. So H2 can be oxidized. We can take H2 gas and give up 2 electrons to form 2 H pluses. And that has an E standard of oxidation of 0 volts. That's kind of the baseline in terms of our oxidation and reduction potentials. All right, so no, that's okay, but can we do better? Can we do better? Yes, we can. Au, well, that can be oxidized. Can has a little bit of an asterisk here because, hey, if you're looking to oxidize gold, that's going to have a potential of negative 1.69 volts. So good luck. It can be done, just very difficult. F2 cannot be oxidized. You're not going to see F+. Fluorine loves its electrons too much. Doesn't want to lose an electron. They only have 6 valence electrons. Li+ cannot be oxidized. Remember, the oxidation state is important. Li solid can be. Li+ cannot. Na solid, though, that's oxidation city. Solid sodium is readily oxidized, and that has a positive 2.71 volt potential. So this is going to be our answer here. The solid group 1 metals love to be oxidized, so they make for very, very good reducing agents. All right, now we're balancing a redox reaction in acidic solution. So the first step is going to be to split these into half reactions. So if we look at these, our reduction half reaction is going to be, so for our manganese in our dimanganate anion, the oxidation state of manganese here, each one is 6+, and in manganese dioxide, it is 4+. Okay, so that's going to be what's reduced. So our reduction half reaction is going to be the Mn2O72 minus going into MnO2. And these balancing reactions are actually the one time in chemistry where I don't like to write out the state of matter because it's not going to help us with balancing these. State of matter ordinarily is very important, but here I think it's okay to omit just because we're going to see very busy. There's going to be a lot of writing in this problem. So the nitrogen in nitric oxide is going from, here it's in a +2 oxidation state. It's going up to a +3 oxidation state, so it is being oxidized. So our oxidation half reaction is going to be our NO, nitric oxide, turning into NO2 minus nitrite. Okay, so now we're going to do each of these one at a time. All right, so first for the reduction half reaction. First, you make sure everything other than oxygen and hydrogen is balanced. So notice here, Mn2 versus just Mn. Well, we're going to need to correct that. So what I'm going to do is I'm just going to put a 2 here because we're going to need 2 of these in order to have an equal number of manganese on both sides. Now, what is the issue? Well, there's not enough oxygens on the right-hand side. There's 7 over here, and there's only 4 total over here. So how do we balance out oxygen? With water. So with 3 waters, great, okay. But wait, oh no, now H+, hydrogen's not balanced. So we're going to add in 6 H pluses over here. Cool, cool. Now, the final thing we're going to do is balance out the electrons. And if we look, the total charge on this side, adding up the 2 minus and the 6 positive charges, this has a total charge of 4 plus. And over here, well, this side's completely neutral. So this is going to be a 4 electron reduction. And voila, that half reaction is balanced. Now we're going to go through the same process down here. We need 1 water on this side in order to balance things out. And we'll need 2 H pluses over here to balance things out. Looking at the total charge on each side of the reaction, we have a total charge of 0 over here and a total charge of positive 1, because we've got this negative charge and 2 positive charges here. So we're going to need 1 electron in order to finish this out. Now then, these are both balanced in terms of half reactions. In order to combine them, what do we need to do? Well, we need to make sure the number of electrons are even in the reduction and the oxidation. You can't have a 4 electron reduction and only a 1 electron oxidation. So, let's see. Since this is a coefficient of 1, we're going to need to multiply everything in this reaction by 4 in order to get these to be even out. So remember, everything is balanced from an atomic standpoint, which means we need to multiply everything in this reaction, this half reaction, by 4. Now, these are good to go, and we can combine them and enjoy. So when we combine these together, we can do a little bookkeeping here. Some things will end up canceling out. And what is that? Well, if we look at water, for example, we have 4 waters here, and we've got 3 waters here. So we can just cross out this water, and we can turn this into 1 H2O. Great. In fact, that's going to be our answer, but let's just keep doing this for posterity's sake. Electrons will always cancel out in any self-respecting redox reaction. What else? Ooh, our H plus. 6 H pluses here. We can get rid of that and turn this into 2 H plus. So we'll get our overall balanced reaction, which is going to be Mn2O7 2 minus plus 4 nitric oxides plus 1 H2O yields 2 MnO2s plus 4 NO2 minuses plus 2 H pluses. And again, the question is, what is the coefficient in front of water? And the answer is but 1. Here we have a classic true-false question. Which of these is false? So A, if a voltaic cell has a positive cell potential, it is spontaneous as written and will have a negative delta G. So positive E cell means a negative delta G, means a spontaneous reaction. So this one is indeed true. Ding! And I'm putting that check there just so this is true. This is not the answer because we're looking for which one is false. All right, the next one says, in a voltaic cell, when E cell equals 0 and delta G equals 0, the system is at equilibrium. That is indeed, ding, true. So we know if delta G is equal to 0, that means that a reaction is at equilibrium. Likewise, if E cell equals 0, that means that there's no more net transferring of electrons. It would also mean a dead battery. C, in order to maintain electrical neutrality in a voltaic cell, anions in a salt bridge flow toward the cathode. What? No, false, wrong. In a salt bridge, the anions migrate to the anode. Really easy way of remembering that. And the cations float to the cathode. So this is false. All right, well, just to round this out and discuss the other options. D, electrons in a voltaic cell always travel from the anode to the cathode. That's true. So I always like to do this little doodle here. So electrons always travel in alphabetical order from A to C. So they always go from the anode to the cathode. Ding, that's true. And finally, a voltaic cell reaching equilibrium does not affect E standard of the cell. Remember, E standard is if you have 1 molar of everything, 25 degrees Celsius, 1 atmosphere of pressure, etc. E standard is a given property of a cell. It does not change even as the cell approaches equilibrium. So this is also true. In this particular problem, we're trying to relate voltage with work. And remember, work is another way of saying delta G. Okay, so we're looking at standard conditions here. So we're trying to find delta G standard, which means we can use E cell standard. And what we're going to do is use the equation delta G standard is equal to negative N times Faraday's constant, F, and E standard of a cell. And this equation works for both standard and non-standard conditions. We would eliminate the standard sign if it was non-standard. Okay, so we're actually given the E standard of the cell. That's 3.4 volts. Cool. Faraday's constant, well, that's a constant. That's going to be 96,485 coulombs per mole of electrons. Great. And then number of electrons transferred in this overall balanced reaction. They were nice enough to give us the reaction here. It's a 1 electron transfer. So that means it's just going to be 1 mole of electrons. Okay, so we are well on our way to solving this problem. Delta G standard is going to be equal to negative that. And moles of electrons are going to cancel out. And our units are going to end up being Coulomb volts. And Coulomb volt is just a fancy way of saying joules. Let's see what we get. So it's equal to negative 328,049 Coulomb volts, which again is a fancy way of saying joules. So if we want to transfer this into kilojoules, it becomes 328 kilojoules worth of work. And there is no negative sign here because it's just asking how much work can it do. So the negative sign implies that it's a spontaneous reaction that can do that amount of work. Okay, here we have to analyze this here Voltaic cell. So first, let's figure out what electrolytes we have in our solutions. So in the left-hand component, we have aluminum nitrate. So this has aluminum 3 plus in it. And then in our right-hand compartment, we have gold nitrate. So this is probably a pretty expensive Voltaic cell. And we've got Au plus. So now what we're going to do is write out the 2 potential reduction reactions and figure out which one is more favorable. So first possible reduction, Al3 plus aqueous plus 3 electrons yields Al solid. And this is not super duper favorable. This has an E standard of 1/2 of negative 1.66 volts. Aluminum is pretty difficult to reduce. In fact, usually when we see aluminum, like in aluminum cans, it's oxidized form, aluminum oxide. So gold, on the other hand, one of our precious earth metals. Boy, does gold love to be reduced. In fact, it comes with an impressive 1.69 volt reduction potential. So now what we do next is choose which of these is more favorable. And in this case, it's pretty clear cut. The 1.69 volts is far more positive than the negative 1.66. So what I'm going to do is I'm just going to write the word reduced. Well, red next to this one. And I'm going to take this reaction and flip it around. So when we flip it around, we get the reaction aluminum solid turns into aluminum 3 plus aqueous and 3 electrons. And when we flip the reaction, remember we flip the signs. This is going to become positive 1.66 volts. And then I like to just scratch out the reduction reaction that we're not using. This is not what's going to happen here. Okay, so here we have our half reactions. Just in order to let them be balanced, though, we want to make sure. So we need 3 times as many electrons in this reaction. So I'm going to multiply everything by 3 so that we have a balanced overall reaction. Okay, and if you're curious, the overall reaction then is going to be 3 Au plus aqueous plus aluminum solid yields Al3 plus aqueous and 3 gold solids. All right, now then, we're looking for standard free energy change. So we're trying to find, with this information, delta G standard. And we can relate this to E standard using the equation negative N F, Faraday's constant, times E standard of the cell. So let's plug in our values. First, let's calculate E standard. It's going to be equal to the sum of the reduction potential, 1.69 volts, plus the oxidation potential, 1.66 volts. So it's 3.35 volts. Now let's plug in everything into our E standard, into our equation to find delta G standard. So delta G standard is equal to negative N, the number of moles of electrons transferred in the balanced overall reaction, 3 moles of electrons, times Faraday's constant, which is 96,485 coulombs for every mole of electrons, times the E standard of our cell, which is 3.35 volts. And so our units are going to cancel out. Moles of electrons will cancel out. And we'll end up getting delta G standard equals negative 969,674 coulomb volts, which is another way of saying joules. So this is equal to about negative 970 kilojoules. And the answers up here actually aren't correct. It should have said how much work can this do under standard conditions. Since all of these have a positive value, delta G has to be negative for a voltaic cell that hasn't reached equilibrium. So anyway, but none of the answers are negative here, so we can tell that it's just kind of an omission there. And so this could do 970 kilojoules per mole worth of work. Pretty notable. That is quite a voltaic cell, and an expensive one with the gold. Alrighty, here we have ourselves a dimensional analysis problem, an electroplating problem. So, first things first, in these problems, always make sure to write out the reduction reaction. The idea is we're taking a metal and we're reducing it into its solid. So zinc chloride, each chloride is going to be minus 1, which means zinc here is in its +2 oxidation state. That's going to be important. So our reaction to turn this into a solid is going to be zinc 2 plus +2 electrons yields solid zinc. All right, reaction done. Next, in electroplating problems, I always like to write myself 2 little reminders. Well, I say little reminders, but they're actually pretty big reminders. And those are, first of all, what amperes means. So, 0.75 amperes. What does that mean? That means that what we're getting here is 0.75 coulombs of charge for every 1 second. So amperes are coulombs per second. Really, really, really important conversion factors in these problems. The other reminder that I like to write myself is what a Faraday is. So 1 Faraday is a mole of electrons, which is equal to 96,485 coulombs worth of charge. So oftentimes we'll have to use both of these conversion factors in order to solve these problems. Now at this point, it just becomes more or less a giant dimensional analysis problem. So we can see here that we're starting with 25 grams of zinc that we're trying to plate. So 25 grams of zinc. Okay, now we're going to need to convert it into the universal currency of chemistry, the mole. So there are 65.4 grams of zinc for every 1 mole of zinc. Now then, this is where the equation becomes really important, because we can see that for every 1 mole of zinc we want to make, it's going to take 2 moles of electrons. So that's going to be our next conversion factor, is 1 mole of zinc necessitates 2 moles of electrons. And then I always like to use coulombs as a kind of a break point in these, because generally speaking, coulombs will oftentimes be a central figure. So for every 1 mole of electrons, we have 96,485 coulombs worth of charge. So I'm going to calculate that. So now let's watch those units cancel out. Grams of zinc cancels out. Moles of zinc cancels out. Moles of electrons cancel out. And we're left then with just coulombs of charge. And this ends up being 73,765 coulombs worth of charge. Now here's where our other conversion factor is going to come into play. Amperage allows us to relate charge and time. So let's do just that. We know that for every 1 second, there are 0.75 coulombs of charge using our conversion factor. And now it's just a matter of getting it into the right units of time. So there are 60 seconds in 1 minute, but we want hours. And there are 60 minutes in 1 hour. So now we do another unit striking out extravaganza. Coulombs cancels out, seconds cancels out, minutes cancels out, and we're left with 27.3 hours. Woo! Answer E. Okay, in this problem, we're asked to calculate the standard potential of a voltaic cell. And we're using the standard notation, which remember, standard notation gives us the anode on the left of this double dash right here, and then the cathode on the right. And just remember that cathode is where reduction takes place, and the anode is where oxidation takes place. Okay, and we're looking for standard potential, so there's going to be no need to Nernst, but also this is under standard conditions because it's 1 molar of everything. So let's write out our respective half reactions. For the anode, for oxidation, we have copper being oxidized in the copper 2+. Now, be careful because copper is one of those elements that has multiple potentials on our table, so it's important to use the right oxidation states. This is +1 going to +2, and that's going to have a voltage of negative 0.153 volts. So that's the oxidation of copper plus to copper 2+. And now, let's look at our reduction. So our reduction is I3- going to I- iodide. So it turns into 3 iodides, and there are 3 electrons. And this reaction is available on your data table. And this has a potential of 0.53 volts. And then just remember, in order to get the E standard, we just have to add together the standard reduction potential of whatever's being reduced, plus the standard oxidation potential of whatever's being oxidized, so we end up getting 0.377 volts. In this problem, we're looking at what happens to the solubility of barium carbonate, so that's BaCO3, as we add in this common ion. So first, let's write out the reaction. This, we're looking to see its solubility. We're looking at it splitting into barium 2+ and carbonate, CO3 2-. So if we add in sodium carbonate, so this is the source of the common ion carbonate. All sodium salts are completely soluble. So the sodium is just a spectator here. It's like we're adding in CO3 2-. And what happens as you add in a common ion? So as we add in more of the carbonate, this reaction would shift to the left, therefore making this less soluble. So more carbonate means a less soluble salt, which means choice A is our winner. In this problem, we're looking for the molar solubility of silver sulfate, Ag2SO3, and we've got a solution of silver nitrate. This has a common ion. We'll get into that in a second. And then we're given a KSP of silver sulfate. If you're not sure where to start, if you're ever given a KSP, I recommend writing out the reaction for KSP. And with KSP, are we making stuff or are we breaking stuff? That's right. With KSP, it's only gonna break apart. It's only gonna break apart. Into, in this case, silver, Ag+, and sulfite, SO3, 2-. All right. So, whenever you're looking for molar solubility, we have, when in doubt, we're going to ice it out to an ICE table. Now then, what's the deal, though, with this silver nitrate? This is an example of the common ion effect. Look at that high budget animation. We have a common ion effect, in effect. All nitrates are completely soluble. So this just means that we have a solution of Ag+. And since there's one Ag+ for every silver nitrate, that means it's going to be the same concentration. So what we're going to do, we're going to do this like a regular ICE table, but we're going to plug in 0.5 molar for our Ag+ concentration. And note that in our reaction, this is splitting apart into 2 silver pluses. But that stoichiometry doesn't matter here because this is coming from an independent source of silver. So all we're going to do is take the silver from this common ion solution and plug it in for our initial line. After that, the rest of this is going to be just like any old ICE table problem. So we're starting off with 0 of the sulfite. For the silver sulfite, we don't care. I always like to include the minus X in molar solubility problems because remember, molar solubility means X. It's going to be plus 2X, so there's where the 2 does come into play, so that the change would involve that stoichiometric coefficient, although we'll see that that's insignificant. It's going to be plus X. So for our equilibrium line, 0 plus X is X, 0.5 plus 2X is 0.5 plus 2X, and we don't care minus X is we don't care. All right, so now we're going to write out our equilibrium expression. That's pretty classic. So our KSP is going to be equal to our silver concentration squared times our sulfite concentration. Remember, solids do not go into this equation. And now when plugging in values, compared to this 0.5 molar of silver present in the solution, will this 2X really make a difference? Well, the answer is no. So to make our calculation easier, we can just say this is negligible. So now let's plug in our values. We have 1.5 times 10 to the negative 14th times 0.5, or is equal to 0.5 squared times X. So we'll divide both sides by 0.5 squared. 0.5 squared is just 0.25. So divide both sides by the 0.5 squared. And get that X is equal to 6.0 times 10 to the negative 14th. And so our answer is going to be D. Because remember, X is the molar solubility, so that's what we were solving for here. Okay, in this problem, we're trying to figure out how we can decrease the E cell of this reaction. So decrease, again, means that we want to become less spontaneous, which means we want a shift to the left. So let's have a look at these options. And before I do that, we'll notice that some of these discuss like the anode compartment here. So it might behoove us to write out the half reactions that are going on in the anode and cathode. And as a little reminder, electrons always travel in alphabetical order. They always go from A to C. I always like writing out this little reminder. So anode's where oxidation takes place, and cathode is where reduction takes place. So what is being oxidized in this particular reaction? Well, we can see the silver is going from solid neutral silver to Ag+. So that's going to be our oxidation half reaction. So the anode, have Ag solid turning into Ag plus, and I'm not including the stoichiometric coefficients here. It's not going to change our answer. So each silver is giving up one electron. And then for our cathode, the reaction is going to be the reduction of oxygen, which is pretty favorable. So that reaction is O2 gas plus 4H plus 4 electrons yields 2 H2O. Now then, let's see how each of these would affect our reaction. Choice A says adding pure water to the anode. So adding pure water means we're going to decrease the concentration of any aqueous species, because if you're adding in water, you're diluting it. So it's not going to affect the solid because it's a solid. It has an activity of 1. It does not change its concentration. But it will bring the concentration of Ag plus down, which will cause the reaction to shift to the right, which will cause the E cell to increase. A shift to the right means an increase in voltage. So we can eliminate this answer choice. The next answer choice says adding more of the solid silver. Well, adding a solid does not influence a reaction based on the Chatelet's principle, right? It's only aqueous species and gaseous species. So adding more of a solid, well, it might allow our battery to last longer because you need the reactants in there, but it's not going to actually cause a shift. So we can eliminate that answer choice. Choice C says adding Cl minus, and then we're given a KSP to the anode. Why is this significant? Well, it's significant because we're told that this is a sparingly soluble salt, which means that Ag plus and Cl minus will readily react with each other to form AgCl solid. So the Cl minus will help pull Ag plus out of the solution, which means the Ag plus would go down, which means this reaction would shift to the right, which means the E cell would increase, which means this is not the answer we're looking for. The next answer choice says increasing the pH in compartments. Whenever I see something about increasing or decreasing pH, I like to remind myself what that means. So an increase in pH means we're making it more basic, right? Because as pH goes up, a solution becomes more basic, which is another way of saying less acidic, which is another way of saying, oops, that's not how you spell acidic. It's another way of saying that the H plus concentration goes down. So that will not affect the anode compartment, as H plus is not a part of this. However, it will affect our cathode, because if the H plus concentration is going down, this reaction will shift to the left. The shifting to the left is becoming less spontaneous as written, which means the E cell would decrease, and hey, that's what we're looking for. The final answer choice says evaporating off H2O liquid. Liquids do not influence reactions based off of the Chatelet's principle, so we can eliminate that answer choice as well. In this problem, we're given both a KSP reaction and a KF reaction, and we're asked to find the solubility of copper carbonate if there is ammonia present to help facilitate dissolution. Okay, so I recommend whenever you're given a KSP and a KF, write out both of the reactions. So for KSP, are we making it or are we breaking it? With KSP, we are, in addition to Penn State, breaking it. So our KSP reaction is going to be copper carbonate dissociating into copper 2 plus and carbonate, CO3 2 minus. Now with a KF reaction, are we making it or are we breaking it? With KF, we're forming it. So for our KF reaction, let's write our products first. Our product is going to be, we're forming this copper ammonia complex thing, to use the technical scientific terms for it. So this copper ammonia complex. And in order to make that, well, we'll need copper 2 plus and 4 ammonias. So if we have copper carbonate and it's present in a solution with ammonia, so when we combine these two together, the copper will cancel out, and we'll get the overall reaction of copper carbonate Cu3 solid, plus 4 ammonias, yields our copper ammonia complex, and that's aqueous. Should have written that before. And carbonate, CO3 2-, also aqueous. Okay, so when in doubt, ice it out. But before we do any ICE table, well, we can just put the ICE here just because we're going to be doing an ICE table. Generally speaking, whenever you want to find molar solubility, that's going to be the key. But how can we get the KEQ for this overall reaction that we made? And generally speaking, anytime you have a KSP and a KF in a problem, you're probably going to be combining them together, just usually speaking. Well, what we can do is we can multiply the KSP of the stuff we broke by the KF of the stuff we formed to get our new KEQ. For this overall reaction. So when we multiply the two of these together, we'll end up getting the KEQ equals 1,150. And again, that's just what we got by multiplying our two respective K values, our KSP and our KF. Now we're going to plug in all the information that we know into this table. And notice in this problem, we're given an equilibrium concentration. Usually in these formation problems, we're given an equilibrium concentration of something. So I'm going to start by plugging that in. That's going to be really useful to us. And then the rest of this, well, let's see here. We don't care about that. And this would start with 0, and this would start with 0, unless told otherwise. All right. Turns out we don't need the initial and the change for the ammonia because we know the equilibrium value. So this part actually doesn't matter. And actually just fill it in with a little zip zap zoop there. This is going to be plus x, and this is going to be plus x. 0 plus x is x, 0 plus x is x. Over here it's going to be minus x, and we don't care minus x is, well, we don't care. So now we can plug everything into our equilibrium expression. So KEQ is equal to our products. So we have our copper ammonia complex. This is 2 plus times the carbonate, CO3 2-, all divided by, we don't include our solid, but we do have to remember that it's the NH3 to the 4th because it does have that stoichiometric coefficient of 4 here. All right, so now let's plug in all of our values. We have 1,150 is equal to x times x, which is just x squared, over 0.5 to the 4th. All right, so we'll multiply the 0.5 to the 4th through. We'll get 71.9 is equal to x squared. Take the square root of both sides, and we'll get that x is equal to 8.48. And remember, x, our change in the solid, that is our molar solubility. So the molar solubility here rounds up to 8.5 molar. In this problem, we have to see which of these 3 chemical species will precipitate out first. And NaCl is not going to be the answer because NaCl, all sodium salts, all group 1 salts, are completely soluble. The NaCl is just the source of a common ion here. So I'm just going to start by eliminating that. All right. So what I'm going to do is I'm going to write out the dissolution reactions that correspond to each of these equations. For the AgCl, it's AgCl, solid, turns into Ag plus and Cl minus. Okay. For PbCl2, it's going to look a little different, isn't it? So for PbCl2, it's going to dissociate into lead, Pb2 plus, and 2 chlorides, 2 Cl minuses. Okay, so I wanted to write out these reactions because whenever you have a KSP, it's important to write out the reactions. But this is going to change our equilibrium expressions. And what I mean by that is if we write out the equilibrium expressions for each of these. So for the KSP of AgCl, our equilibrium expression is going to be Ag plus times Cl minus, right? For our PbCl2, our KSP is going to be equal to Pb2 plus times Cl minus squared. And it's going to be the same general math, or general setup for CuCl2, since it breaks into two chlorides. So it's going to be KSP is equal to Cu2 plus. I'm not explicitly writing out the reaction here, but it follows the same general idea as the PbCl2. Okay, so these are our three equilibrium expressions, and now basically what we're going to do is we see that we have a source of Ag plus, Pb2 plus, and Cu2 plus. We're going to plug in those values, and we're going to see which one will take the least amount of chloride to make it precipitate. So basically at this point, we've done most of the work. We're going to do a little plug and chug action here. So I'm going to move this over to give us some more room to work with. Okay, and let's start with the silver chloride one. So our KSP is 1.8 times 10 to the negative 10th. So that's going to be equal to, we're told that the silver concentration, so the silver concentration is equal to 2 times 10 to the negative third. And we're trying to find how much chloride it'll take. So dividing both sides by 2 times 10 to the negative third, we'll get 9 times 10 to the negative eighth. So that is the concentration of chloride we would need to reach saturation. Remember, once you reach saturation, if you add even a little more, we're going to get a precipitate. So in these problems, you're basically calculating how much of the common ion, the ion that's in common between these, in this case, 3 different salts, it's going to take to reach saturation. Because whichever one reaches saturation first, that's the one that's going to precipitate out first if you keep adding chloride. So now let's do the calculation for the lead chloride. So 1.7 times 10 to the negative 5 is the lead 2 plus concentration. Cool. And then, that's the K for this reaction right here. And then our lead 2 plus concentration is 5 times 10 to the negative fourth. So let's plug that in. And then it's going to be times Cl minus squared. So dividing both sides by the 5 times 10 to the negative fourth, we'll get that the Cl minus squared concentration to reach saturation is equal to 3.4 times 10 to the negative 2. Then we're going to take the square root of both sides and get that the Cl minus concentration that we would need to reach saturation is 0.18. And that's an awful lot of chloride. All right, so now let's do this for the last one. So our K value is 1.7 times 10 to the negative 7th. And that's going to be equal to, we're given our copper 2 plus concentration, which is 2.5 times 10 to the negative 5th molar. And then we have Cl minus squared. So we'll divide both sides by the 2.5 times 10 to the negative 5th. So we'll get that the Cl minus concentration squared is equal to 6.8 times 10 to the negative third. We'll take the square root of both sides. And we'll end up getting this chloride concentration needed to reach equilibrium, saturation here, is 8.2 times 10 to the negative 2. So which one takes the least amount of chloride to reach saturation? Which one is going to form a precipitate first? Well, that's going to be this one right here. Because look, it only takes 9 times 10 to the negative 8th molar. That's such a small concentration. It's a lot smaller than the amount that it would take of the chloride to make the lead chloride precipitate out and the copper chloride precipitate out. So our answer is going to be that AgCl will precipitate out first. in this problem, we have a concentration cell, neat. And remember, the idea behind a concentration cell is the E standard is going to be 0, because if we look at our two half reactions, so our electrons are flowing, they always flow from anode to cathode. So I'm going to write out the reduction reaction first. We have nickel 2 plus, aqueous that we are reducing to form nickel solid. So this has an E standard, 1/2 of negative 0.28 volts. Okay. Now, meanwhile, in our anode, we're oxidizing nickel. So nickel solid going to nickel 2 plus and 2 electrons. That's going to have a standard potential of positive 0.28 volts. So if we add these two together, we'll get the standard voltage of the cell, which is a, impressive, quote unquote, E standard of the cell is equal to 0 volts. So at this point, you might say, what? Well, then how can there be a voltage? And the idea is that we use different concentrations in order to facilitate the flow of electrons. So what I mean by that is this cell will keep going until we have an equal concentration of nickel 2 plus on both sides. So there actually is, in effect, an overall reaction that takes place, because in our in our concentrated compartment, we want our nickel 2 plus to go down. That's where it's being reduced. And the anode is going to have our dilute solution, because that nickel 2 plus is going to need to go up in order for the two concentrations to equilibrate. So we actually do have an overall reaction, and that overall reaction is the concentrated nickel 2 plus is going down, while the dilute nickel 2 plus is going up. This will keep going until they have equal concentrations. So we can actually use the Nernst equation to figure out the voltage of the cell. Remember, the Nernst equation is E cell is equal to E standard of a cell minus 0.0592 divided by N times the log of Q. And it's this Q here that's actually going to end up giving us a voltage. So let's plug in our values and see what we end up getting. We have, actually first let's solve for Q. So our Q is equal to the dilute nickel 2 plus over the concentrated nickel 2 plus. Let's plug in our values here. Our dilute is 1 times 10 to the negative third. So 0.001. And our concentrated is going to be just 1 molar, which means our Q is just equal to 0.001. Okay, cool. Now let's plug everything into the Nernst equation. Oh no. Sorry, I hit pause on the recording when I didn't mean to. So just to catch up here, just in case, I apologize if I'm repeating myself here, but our Q is equal to the dilute concentration divided by the concentrated concentration for nickel 2 plus, which ends up equaling 0.001. So now we plug everything into our Nernst equation. Our E standard is 0. Our moles of electrons transferred in the balance reaction are 2. And here is our value for Q. And let's see what we end up getting. We end up getting that E cell is equal to 0.089 volts. So concentration cells work because the dilute side becomes more concentrated and the concentrated side becomes more dilute. So in effect, what we end up getting is this, it's almost sort of like an electrochemical osmosis of sorts. So we end up having this electron transfer to have them be equal in concentrations in both compartments. So pretty cool and some pretty nifty applications.